All right, hello everyone and welcome. Today, we're jumping right into a huge challenge in computer science, one that's happening inside your devices every single second. How do you get all these different computer processes to work together on the same stuff without, causing a total meltdown? Let's get into it. So to get our heads around this, think about it like this. Imagine you and your friend are in a Google Doc, editing the exact same sentence at the exact same time. You're trying to delete the last word, and at the same instant, they're trying to add a new word at the end. What you get is, well, it's a total mess, right? Just garbage text. That chaotic result, that's what we call a race condition, and it's a constant threat inside your computer.
Okay, so in the world of computer science, that sentence you were both fighting over, that's what we call a shared resource. And the piece of the code that's actually touching that sentence is called the critical section. The whole challenge here, the critical section problem, is about building a system, a set of rules, so that when one process is messing with that shared data, everybody else has to wait their turn. Simple as that.
So how do we actually fix this? Well, before we even start looking at the cool tools we can use, we need to lay down the law. Any good solution, and I mean any solution, has to follow three basic essential rules. You got to think of these as the absolute, non-negotiable laws for preventing digital anarchy. And here you have it, straight from the source notes. These three conditions, they aren't just, nice ideas or suggestions. They're rock-solid requirements. If your solution violates even one of these, it's broken. So let's break down what they actually mean. First up, mutual exclusion. Super simple idea. Only one process gets the key to the critical section at a time. It's like a one-person-at-a-time rule for a room. This stops that data corruption we talked about. Second, progress. This rule basically says no gridlock. If the room is empty and a few processes are waiting to get in, you have to pick one. You can't just leave them waiting forever. And finally, bounded wait. This rule prevents starvation. It means if you're waiting in line, you're guaranteed to get your turn eventually. There's a limit to how many other processes can cut in front of you. So, bottom line, no chaos, no gridlock, and everybody gets a turn.
Okay, so we've got the rules. Now, let's open up the toolkit that programmers actually use to enforce them. We're going to start way down at the foundation, with the hardware itself, and then build our way up to the smarter software tools.
Way down at the very bottom, the CPU itself actually gives us a hand. It has these special instructions that are atomic. Now, atomic just means they're absolutely indivisible. Once an instruction like test and set starts, the hardware guarantees that it will finish completely with no other process getting a word in edgewise. This is so important because it lets a process check a lock and grab it in one single uninterruptible move. It's the fundamental building block for everything else.
Now, building on top of that hardware bedrock, we get to one of the most famous tools in the box, the semaphore. The easiest way to think about a semaphore is as a kind of digital gatekeeper. It has a counter, and it controls access using two main commands, wait and signal. When a process wants to get into the critical section, it has to call wait, and when it's all done, it calls signal to let the gatekeeper know it's leaving.
Right, so not all semaphores are the same. You've got two main types. First, there's a counting semaphore. Its value can be any number, which is perfect for managing a bunch of identical resources. Think of it like a counter for the number of available parking spots in a lot. Then you have a binary semaphore, which you'll hear called a mutex all the time. Its value can only be 0 or 1, locked or unlocked. It's like the key to a single bathroom. Simple, but incredibly effective for that one-at-a-time rule.
So semaphores are awesome, right? Super powerful. But they have this one tiny little weakness. And that weakness is us, the programmers. What do you think happens if someone writes the code to call wait to grab the lock, but then they completely forget to call signal when they're done? Well, that resource is now locked, forever. And every other process waiting for it is just stuck, permanently. And that problem leads us directly to our next tool, the monitor. A monitor is a much smarter, higher-level solution. Instead of just giving programmers a lock and hoping they use it right, a monitor bundles the shared data and all the rules for accessing it into one safe little package. It's kind of like a fortress. The data is locked inside, and the fortress walls themselves make sure only one process gets in at a time. And this is basically how it works. Everything, the data, the operations, it's all encapsulated. If a process comes along and tries to get in while someone else is already inside, the monitor just automatically puts it in a waiting queue. The programmer doesn't even have to think about wait or signal. The whole structure takes care of it, which makes it way, way safer and less prone to those silly human mistakes.
All right, so we've got this awesome toolkit, right? Hardware stuff, semaphores, monitors. Now let's see how we can actually use them to tackle some of the classic real-world problems you'll see all the time in operating systems.
First on the list, the producer-consumer problem. This one is a total classic. Just imagine a chef, the producer, who is constantly putting food onto a conveyor belt. That belt is our shared buffer. At the other end, there's a waiter, the consumer, who's taking the food off. The challenge is, how do you make sure the chef doesn't try to add food when the belt is already full? And how do you stop the waiter from trying to take food when the belt is empty? Semaphores are absolutely perfect for this.
Okay, next up, the reader's-writer's problem. Think about something like a shared file or a database record. We want to let as many processes as we can, the readers, look at the data at the same time. That's fine. But if a process, a writer, wants to come in and change the data, it needs to have exclusive access. Nobody else can be reading or writing. It's a tricky balancing act, and solving it is a great test for any of these synchronization tools.
So when you step back and look at all this stuff, the rules, the hardware, the software tools, you start to realize something pretty cool. What's happening inside our computers isn't just random chaos. It's actually a beautifully organized performance.
So what's the bottom line here? All this process synchronization stuff, it's like the unseen conductor of a massive orchestra inside your machine. It takes all this potential for chaos and conflict and turns it into a coordinated symphony. It's the magic that lets you have a web browser open, music playing in the background, and notifications popping up, all at the same time without everything just crashing. These are the unsung heroes of multitasking.
And that brings us to one last big question for the future. We've gotten pretty good at these ideas on computers with 2 or 4 or 8 processing cores, but what happens when our computers have hundreds or maybe even thousands of cores all trying to work together? How do these classic ideas, mutex, semaphores, monitors, how do they have to change and evolve to handle that kind of massive scale? That is the next great challenge in Taming the Chaos. Thanks for joining me.